It's just pointed at me.
Can they hear us?
Yeah, so don't say anything.
Can you opt out
Now
of
it's
school?
recording. Hey guys, it's
You have
me.
a choice.
Oh my god, I
Okay. Now, yesterday I started teaching configuration, so let's just start again so everybody can do it. So if you look at this periodic table, it's really just interesting that it models all the stuff about quantum theory in terms of the structure of how the electrons are arranged. So let me just start doing it first, and then I'll see if you start to pick up the pattern. That's what it is about. It's just using this to establish a pattern. And once we can do that, I'll make it more clear what we're doing it for. So we said hydrogen has only one electron. And we have labeled these regions that you see, S, P, D, and F, based on the electron clouds having certain shapes of energy. But the main energy that the electrons are filling are based on layers or shells. And that's what these period numbers are for. So this group of numbers going down that list the rows are what we call the period. But what they really correspond to is the energy level or the layer that the electrons are going into. So if you pictured a nucleus, then n equals 1, the electrons are going in at some certain average distance from the nucleus. And then if I go and fill that layer, because there's rules that establish how many electrons fit, then I have to start filling them in a new layer, et cetera, et cetera. And so what this is telling us is we're building up atoms. The atoms keep getting bigger because the rules established by quantum theory show us that the electrons have to go in a certain way and in a certain kind of structure. So that's the first kind of level you have to understand. The next thing is that it's not simple rings like Bohr thought, but that it's these electron clouds. And these clouds are just regions or orbitals where the electrons hang out, and the different letters describe the shapes of those orbitals. So I tried to show you yesterday, if it's an S-type orbital, the electron cloud looks spherical. If it's a P-type orbital, the cloud looks more like that. If it's a D-type orbital, the electron cloud looks something like this. And then I won't even bother with the F orbitals, they're hard to draw. So the idea here is that the periodic table also reveals another interesting fact. And that is that each sub-level, as these are described, these are called sub-levels, S, P, D, and F, because they're made up sometimes of more than one orbital each. And we had established that the sub-levels each have a certain number of orbitals. But you don't have to memorize that. It's built into the periodic table. Check it out. For every pairing, there's one of these types of orbitals. Because if you look here, there's always 2 electrons worth, and each orbital, as we said yesterday, can hold up to 2 electrons. By that rule, if this is the p block, P sublevel, how many orbitals are represented in this section?
6.
Not orbitals, there's 6 electrons. So 1, 2, 3 orbitals worth, which is why it holds 6. Now, here in the D block, if you just cut in half the number of elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it implies 5 orbitals. 1, 2, 3, 4, 5. And then at the bottom, I won't break the little brackets, but it's 7. So what I'm trying to establish here is that everything I'm asking you to remember doesn't have to be memorized. It has to be decoded from the periodic table. Now, once we get all that, we remind ourselves of some of the key rules. One key rule was the Pauli exclusion principle, which tells us that each orbital can hold, at most, 2 electrons, which is why there's 2 electrons worth here, 1, 2, 3, 4, 5, 6 here, 10, and 14. And now, instead of, if any of you are computer programmers, if you've ever done computer class, you'll know that the computer only understands one language. It's called machine language, zeros and ones. So if you had to program a computer to play your favorite video game in machine language, you would literally have to write everything out in zeros and ones. That would be almost impossible. So what do? They write languages that make it more user-friendly for us to interact with machines. But in the end, those languages have to translate back to zeros and ones for the computer. In a similar way, quantum theory spits out a bunch of numbers for each electron's possible energy state. And what we've done is we've kind of layered out a different way to describe it so it's more compact and easier to look at. So in the case of hydrogen, here's what we know. Hydrogen has one electron. And in its lowest energy state, that electron exists in the first energy level in a spherically shaped cloud that holds the one electron. That's what this is describing. This represents, and I tried to sketch it yesterday on my pad, I'll do it again here, a positive center, a spherical electron cloud, and within that cloud, one electron zipping around. That's what this is telling me. Further, if I was looking at the quantum calculations, which we don't, I could tell you the energy of that electron in this state. I could also tell you that if it absorbed a certain photon, it would jump into a different, broader cloud state. And then if it fell back, it would emit that photon. All of that comes out of quantum theory. Right now, we're just focusing on the ground state, which means the electron's going into the lowest place they can go. It would be, again, analogous to filling a glass with water. If you put some water in a glass, it sits at the bottom. That's its lowest state. If you shake the glass, doesn't the water jump around? And then when you stop shaking it, it falls back to the bottom. When you energize a ground state atom, its electrons can vibrate to higher orbitals. But if you stop messing with it, it falls back to the ground state and shoots out the instrument. That's the essence of this theory. Now what we have to do is establish how to use this to write those patterns. So I'm going to keep going from hydrogen. Helium is still in the first row. But, actually, let me go kind of following. Oh, that won't fit. I'll just go with where I'm going. Helium is still in the first row. So notice that every time I put this coefficient, I'm describing what row the element is in. That's really telling me what energy level the electrons are going into. I'm still going into the same spherical orbital that I started with hydrogen, because I'm still over here in the S block. But this time there's a total of 2 electrons. And I told you yesterday that one of the rules of quantum mechanics, the Pauli exclusion principle, suggests that when 2 electrons share an orbital, they have to have this opposite property of spin. And I was trying to represent that with arrows going up and down. So this is 1 electron, this is 1 electron. So while I'm teaching you this, I'm going to parallel another thing, another way to show this. So this is the configuration. I also want to show you, let me just abbreviate this, econfig. Next door, I'm going to write what's called an orbital diagram. It's not what you think. You don't have to draw a bunch of clouds. We're going to draw some lines and arrows that help us visualize how the electrons go in a little bit more here. So I'm going to draw them across. Sometimes they're drawn vertically. It doesn't really matter. But the 1s orbital of any atom, really, I'm going to use the line to represent an orbital. So this is the energy level, which again corresponds to the row I'm filling. This is the sublevel, which describes the shape and energy of the cloud. And then this is the orbital. So this line is going to represent my actual cloud, so I don't have to draw these. So I don't have to draw that. Okay? Now when I want to show electrons going in, I'm going to use those up and down arrows so I can kind of visualize the Pauli exclusion principle working. So right now, hydrogen only has 1 electron, so I'm going to use an up arrow to represent it. This is the same thing as saying this. It's just a little bit more detail. How do I mean? Well, when I write it for helium, instead of one electron, I have two. That means I have to put two arrows on this line to represent the two electrons. But what I really want you to see here is that it has to be drawn one up and one down. That's what the Pauli exclusion principle is suggesting. If they were both pointing the same way, that wouldn't work. That's the point. So, questions so far? Can you see where I got what I got? And if you're not sure, you have to ask, because I'm just going to keep adding to this layer by layer. Yeah?
Does up mean anything?
So again, that kind of corresponds to the idea of a quantum mechanical property that we can't really define with a classical sense, but the closest we can say is if the electron is a little negative ball and it's able to rotate along its axis or around its axis, there are two ways it could rotate. One would be clockwise, one would be counterclockwise. And what that does is it imbues the electron with some kind of magnetic property in terms of the way electrons interact. And when they're in opposite sense of spin, they line up in a more favorable way. So it kind of relates to that. Any other questions about how I'm setting up the numbers, the letters, anything? It's just a code that I'm teaching you right now. Anything that I can do to clarify it further before we go on? Or do you think just seeing more of it might start to catch you? Let's try it. So when we get to lithium, we already know we're going to have to go all the way from the beginning and work our way to 3 electrons worth into the atom. But the issue is, all 3 don't fit in the first level. The rules of quantum mechanics are kind of on display right here in this picture, because it tells us I have to start filling a new row to put the next electron. So 1s2 is still there, because those first 2 electrons always go there. That's the bottom of every atom, closest to its nucleus. But now I have to go to the second row, so that's where that 2 is coming from. And I'm still in this S block, so I'm still in a spherical type of shell, but I have one more electron to add. The third electron then looks like this. So again, what this is telling me is that the atom's size has expanded because I've put the third electron in a bigger, farther away, higher energy cloud. And again, it's these rules that told us that the atoms are following this kind of pattern, instead of all the electrons just jumbling together in one layer. So writing it here, I still have the 1s with 2 arrows in it, but now I have to start a new layer. Again, there's only one orbital and one more electron. Let's keep going down the second row. Beryllium is our next character. Can you guess what this term is going to look like, this code?
It's going to have a 2 at the end.
Good.
Same thing, but with a 2.
So 1s2, 2s2. And if I write this line diagram, or orbital diagram, once again, we're going to get pairing that looks like that. Now, when we get to boron, we're still in the second row, but we have to jump across to this next section, because it turns out that quantum mechanics reveals that the second energy level breaks into 2 different types of energy clouds, 2 different types of orbitals, S's and P's. First level didn't have that. Second one does. So now when I go to boron, I still have to fill everything I had before, and now I got to be careful. I'm in the second row, but now I'm in a different type of orbital, the p orbitals. So instead of 2s,
P.
it's 2p.
1.
And there's only one. Very good. So you're starting to see the pattern.
Oh, no, I'm just looking at what we did yesterday.
Right. Which is the pattern. Now, you're going to notice, in this case, when I write the 2p subshell, why did I write 3 lines? What am I trying to represent? The 3 orbitals. Excellent. And we're there. Now the rest of the second row, just to save space, because I can't keep writing, I'm just going to keep erasing this one and changing it. Is that okay? And you guys can keep writing a list. Yeah.
So do you, for like, when you have like the 1S and then the 2S,
Huh?
you just keep, do you always have to add the 1S and the 2S?
Yep.
And then go
And what I'm going to do, she's asking, do I always have to start from the beginning and keep adding on?
Yeah.
Yes, because we're building up the atoms bigger and bigger as we go.
So for every single one after this?
Yes.
It's always gonna be 1S2?
Exactly.
I get
Go ahead.
it.
Oh.
So it's gonna be 1S2?
I don't get the
It's
error.
always going to start with 1s2.
I think the error.
It's like asking me if I'm going to build a series of hotels, is there always going to be a first floor?
No.
Yes. You can't build starting at the third floor.
What's that last year?
Okay, maybe in space.
Maybe like if it's just pillars for the
Yeah, like mypillar.com, I get it. Okay, now, after boron, we go to carbon.
Okay.
But now, the last kind of quantum rule that we have to understand pops in. Because look at what's going to happen next. We have a couple choices here. The second electron in this region can either pair up with this one or take its own. What do you think is going to
Oh,
happen?
wait, can you say that
It's
again?
gonna pair up, because it can
The
hold
second
two.
electron has a choice. It's either going to be able to pair up into this cloud or take a cloud of its own.
It's paired up.
I think it wants to be unique.
Let me give you what I think is a good analogy that applies to everybody. So let's say you go into a bathroom and there's 3 stalls.
Oh God.
It's on, it's on.
One by
And
yourself.
well, be careful, these in 3 dimensions are all equidistant from each other. So really these are all equally distant. So don't think of this as being farther than that. But if you walk into a bathroom stall and somebody's in the first one, is your first instinct to walk in and say, slide over, we're sharing? No.
Yeah.
My first.
Okay, some of you
is to
might.
go to the third one.
You're probably gonna want your own.
Does it always do that? It always goes on its
I
own?
thought it was.
When the orbitals have equal energy like they do here,
You know, sharing is caring.
when they're in the same sublevel,
Close.
then yes. This is called Hund's rule, and I'm not gonna really write it out in words. I'm just gonna tell you that the electrons will pick their own orbital if they have equal energy, like if they're in the same sublevel, before
What
they
if it
pair
was
up.
boron and oxygen?
We're getting there. So after carbon is nitrogen, right? That's just gonna add a new one. And that also gets its own,
But it's in a different orbital.
because it's got a separate orbital to occupy. But now I'm gonna make the analogy one step more disgusting.
Oh God. Please no.
When you get to oxygen, and you add a 4th p electron, now we have another choice. Do we go all the way to the next row? The
No.
next floor? Or do we say, sorry, we're sharing?
They're sharing.
In other words, you've got the worst case of explosive diarrhea you've ever had in your life.
Oh God.
You barely made it to this bathroom and you found all the stalls open or
It's gotta go
occupied.
down.
Like, sorry bud, move over, I gotta go.
You're gonna go for the first one.
Because you're not gonna make it to the next floor. All right, this is not what really happens, but at least it gives you an image.
Can it happen?
It's gotta pair up.
Sure.
And it's
Electrons
paired
with
down.
explosive diarrhea happens all the time. So now we're gonna be forced to pair up as where the next electron goes. And so oxygen has 2 unpaired electrons. But these 2 pair up. And now we can finish up, because after oxygen, we go to fluorine, which has a 5th p electron. Do you see how I'm getting the number 1, 2, 3, 4, 5?
I do.
Yeah.
And then that forces a pairing. And then finally, when we get to the last element in the row, neon, we get to 2p6, and that fills it up.
2p.
And I want you to notice something interesting. Helium has a filled shell, meaning the entire row is done. The next time that happens is neon, also a filled shell. And what do we know about the elements in this family? Chemically, they're the noble gases. What do they do?
They're very noble.
Yeah, but noble here means they're unreactive.
I messed up somewhere. I skipped a line.
So what's interesting is we already start to see a connection between property and configuration. that it seems like elements that have their shells completely filled in a given level are not very chemically active.
I skipped one.
Wait, why isn't beryllium a filled shell?
Well, it's a subshell that's filled.
You're right, no.
The shell is the entire row, right? So the second energy level is broken into sublevels, but it's not a whole shell until you fill all the sublevels in.
Oh, okay, that makes sense.
Right? The shell is based on the coefficient.
Wait, what is the coefficient again?
It's the energy level we're filling, and on the periodic table, it's the row that we have the elements in. So it corresponds to both of them. Now, if this are starting to clear up at all, we should be able to do the third row quite easily because it's just a repetition. So let me kind of do a rapid fire version of the third row. I'm going to erase because I need the space.
That rhymes.
I know. So there you go.
What is that little 3 you put at the end?
The what?
The 3 looking thing, like you wrote like neon, there's like a
I'm thinking about mine, that's it.
What did I write next to me on? Oh, the 3 was me about to start the next row, and I said, no, we're not going to start the next row, we're going to pair up.
oh, okay.
He's probably.
Now we're going to start the next row because once you fill the second energy level, the atom has to expand again. It doesn't have space to accommodate any more electrons. So now, if I start at sodium, can you tell me everything I have to do to get there?
Do the same thing you did. Put a
So
3, no.
first
no.
1s2,
No, that doesn't.
Yes.
Oh, never mind.
then 2s2,
Casey's got it.
then 2p6. That's everything up to neon, right? So this is us back at neon, but what do we have to add now? Where do we go next?
3 something 1. 3
What? Well, the something is
S, yes.
3s1.
S1. Yeah.
Painted it.
Now,
No,
That's a lot to write when you get long.
well, that's why I'm about to shorten it for you.
Oh.
I thought I'll skip this one.
So this is a good time for us to kind of show you how we can write this in a condensed format. And then I'm just going to spend a little more time building up through a couple little tweaks that happen along the way. But for now, check this out. This column is special because it represents filled shells. So what we can do to condense the configuration is you can bracket all the parts that lead up to one of these elements, one of these noble gases, and then use it to represent that part of the configuration. Meaning, instead of writing all this, we are allowed to represent sodium as follows. This is called the condensed configuration.
What if you represented sodium as Na and then in brackets Na?
You can't do that. Further, you're only allowed to use these elements for the shortcut. You can't be like, okay, I'm going to do aluminum, so I'm going to say magnesium and then that.
Oh,
No.
then could you represent neon as neon and then
No.
in neon?
Neon has to show its outer shell. And that's why the reason why we do this is because this portion are known as the core electrons. They're inside behind the outer shell. The outermost shell is called the valence shell. And that becomes super important when we do bonding. Because valence, the outer shell is that part of the atom's electrons that are most active, most manipulable, easiest to push around, and therefore the ones most involved in bonding. So let's continue, and let's write in the diagram here. And that's where we left off, but now if I go through the rest of this row, I can build off of this. And as a result, instead of sodium, if I want to go to magnesium, what's the only thing I have to change?
Make it 2.
Make this a 2, right? And then this pairs up. And then you can see once I get past magnesium, we repeat to argon that whole sequence of not 2p, but since we're in the third row, from S we go to 3p. And we're going to have 3 orbitals there as well.
Is it gonna be the same thing where it's
Same pattern.
down, up, down, up?
I know. So now, just to help you visualize this, let me put this up. I think it's a good time to put this up for you to visualize how the pattern looks. And I want you to notice if you see anything weird about this pattern. So this is just kind of mapping it all out. But there is a couple of weird spots I want to see if you notice.
Why that D6?
What's that?
Why that D6? Why not 7?
Ooh, you notice.
Wait, why is everything with down one?
Ah,
Everything with that
It's
one.
magic.
this is interesting.
No.
So the first time we run into a wrinkle,
Wrinkle.
a wrinkle in time. The first time we run into a wrinkle is based on the fact that the orbital clouds themselves have associated with them a degree of energy. And as you go from the s orbital types to the p to the d to the f, the energy gets higher. And so the filling order, the order in which the electrons occupy orbitals, sometimes goes out of order. The good news is it's easy to put this into your brain because
Really bad.
the S and P always follow the row, okay? So I'm gonna write it like this. S, and usually when I'm numbering the rows, I use N for the number. So S and P always follow what row I'm filling. The d orbitals are always one row behind. It has to do with the way the orbitals' energies work out. I don't want to get deep into it because I think you're just going to get confused. And the f orbitals, if you'll notice, don't start until we get to this position here, where it tells us to move to this spot. If you remember on our periodic table, element 57 tells us to shoot down to the section at the bottom, the f orbitals. This is always going to be 2 energy levels behind. Again, once you see the pattern, it's really not that hard to do.
So how do you write it?
I'm going to show you now. So first, let me go back to just the periodic table I had up. And I'm telling you, once you do this a few times, it becomes really easy. So I'm just going to do this one kind of in rapid fire mode. But first, let's just get up to calcium, where we haven't hit the wrinkle yet. So if I wanted to go to calcium, and I want to do this kind of like some kind of old druid cult. So I'm going to point to the terms and write them, and I want us all to say them together like 1s2, 2s2. Ready? So let's do calcium like a cult. I'll start and you guys chime in. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Good job. First 20 elements done.
We're so
Wait, how many elements?
Hunter?
So you could finish argon in brackets.
Where's my guy?
You could have done argon and then just 4s2. But I'm doing it the long way so you can see the pattern.
Wait, what do you mean? So you could have done CA and then.
You could have
right,
taken
yeah.
this piece
Yeah, I got it. And turned it into.
and called it
You
argon.
knew
I
it.
got it.
I knew it.
So you could have written this as calcium is argon and 4s2. Yes, sir.
When you're writing noble gases, can you write argon equals argon?
No,
Oh.
that's what he
What?
said. You'd have to at least show the outer layer. You could write neon and then just the last of the row.
God, wait, I feel like it's over different.
All right, now, when we do scandium, it's all this again, but this time, we're entering the d orbitals for the first time, but instead of 4d, it's simply 3d. It's 1 energy level off, 1 row off. So for scandium, you'd have 3d1. That's all. That's the wrinkle. But then when we finish all this, we're back to matching our rows. So I'm not going to write all of them, but let's get to zinc. Because if I was doing zinc, I'd have argon, 4s2, all the 3ds would be filled, so it would be 3d10.
It's at the weight and
Go ahead.
first.
Where do I get what? The 10?
Oh, wait, never mind.
1, 2, 3, 4, 5, 6, 7, 8, 9, 100. I mean 10.
1, 2. That was good. I have a question.
Yeah.
For,
I'm good.
For neon, you said that the ones there you can use only the outer layer. What does that mean? Like, how would you write only the outer layer?
Oh, so if you wanted to write argon, you could say argon is neon and 3s2, 3p6. This is the outer layer or the valence shell.
Just the.
Yeah, that's the shortcut. But just for fun, I'm going to do a couple more the long way just so you can see it happen.
I don't think we want to see the fun.
Oh yeah. Oh, you're all about fun.
no.
Is it 7th row?
Yeah, I'm going to do one from there.
I don't. Wait, hold on.
Okay, great.
I did not say it could be like this long.
So this time I'm going to go to barium
Separate.
because he's dead. Ha! I'm going to go to
Oh,
barium.
you.
I don't get it. What do you mean?
Bury him underground.
No, because I took the
Oh, bury him. Okay.
Yeah, and then you get 2 beats.
All right.
Okay.
I shall now.
And then she at the beginning of the first.
She's just taking notes.
Wonder why? Wonder why?
Isn't it right there? Like everything we need to write?
Yes, that's what I'm saying. This website establishes it all.
Can I just use that then?
For now, but eventually you have to do it off the periodic table. All right.
What's the
No. Actually, this would give you some answers that I don't agree with because there's a lot of exceptions to the rules that I'm not asking you to know. I'm just asking you to follow a rule. Now watch me do barium with you, but I'm going to do it a little bit faster this time. See if you can keep up with the terms as I say them. 1 S 2 2 S 2 2 P 6 3 S 2 3 P 6 4 S 2 3 D 10 4 P 6 I'm up to here 5 S 2 4 D 10 5 P 6 6 S 2 just like that, we're more than halfway through the table. Just for now. All right, let's go to each term. That's good. Let's go to each term.
I'm not even right.
Pick me any term.
Take what?
Pick me any term, and I'll show you where it came
The
from.
last one, Lawrencium.
All of it?
Yeah, all of it.
1s2 came from 1 S and 2 elements.
Oh, that makes sense.
2s2 came from 2 S, because we're in this section, and 2 elements.
No.
2p6, since this is the p block, since we're in the second row, 2, since it's p, it's this section, and there's 1, 2, 3, 4, 5, 6 that I'm covering. That's 2p6. 3s2 is because I'm in the third row in the S block and I'm doing 2 more elements. That's 3s2. Then this is 3p6 because I'm in the third row still. I'm in the P block and I get all 6. Here, to get to calcium, I'm in the fourth row, 2 elements in the S block. That put me here. Here's where the first weirdness comes in. It's just the row is 1 level behind. So when I get to the D block the first time, I'm just 1 behind this row number. So instead of 4D, it's just 3D. So 3D, because it's D, and I'm 1 level behind, and there's 10 elements. And that's how I got to D10. If I had stopped here, it would be D4, D5, D6, D7, D8, D9. But if I fill the whole thing, it's, yes? Okay. Anyone else? Should I? Yeah.
Oh, I was just gonna ask, can we do Lawrencium?
Well, I'm going to get, I think I'll do uranium. It's the same idea.
Oh, the red team's the last
Oh no, the last one's actually the OG.
No. Did it just come down?
Oganessium. All right, now.
Listen to me.
Now, I'm going to go, oh, yeah.
Why on the periodic table are some of them not like colored in?
Oh, these are the synthetic elements that are produced in atom smashers that don't exist in nature. So they're not
That's kind of
stably found in nature, they've been created in the lab.
Man-made.
Man-made. All right, now, watch how we get through uranium the long way, then I'll show you the short way. No, this is a good one to have because it really gives you the entire pattern.
But like, do you have to?
I'll even make it harder on myself and start over.
Okay.
You didn't have to do that.
Now I'm gonna go really fast.
Oh,
Can you like slow down?
Do you have this memorized?
Just try to keep up.
Why can't he?
I'm old, I got a bad knee, I can't breathe with a mask on. If I can go this fast, so can you.
Oh, you memorized.
This is the first time you've been saying it.
This isn't the first time you've written letters and numbers. I'm just saying write the letters and numbers with me.
This order.
Ah, whatever.
Order.
And
See, I can't read.
I gotta give myself a little bit more runway.
I'm not supposed to write the all.
Yeah.
Wait, which element are you doing?
Sideways.
I'm gonna be right.
Uranium.
He's so
I
funny.
gotta warm up.
He is so
Or
funny.
right next to the microphone.
1S2,
Oh my God.
2S2,
Say it again.
2P6, 3S2, 3P6, 4S2, D10, 4P6, 5S2, 4D10, 5P6, 6S2. I just got us back to barium.
Wait, can you slow down real quick? Can you?
I have to.
My world.
Write this down.
It's barium.
Hold on, I'm back.
Hold on.
I think I'm gonna be the one you bury.
Oh, no.
Okay, now,
Wait, hold on.
hold on.
You're not done.
Fine.
That was so funny. That was so funny.
What did you do?
Hold on to the word on.
These jokes just keep getting better.
Where's the word on?
Yeah.
I see it.
He erased it.
Oh, of course. That makes sense.
Yeah.
Wait, I'll post
Now,
it.
remember, at this point, whereas the D's were one whole level behind,
These are
we're
two.
about to get propelled into the F orbitals.
It's two.
Why are those all the way at the bottom?
We've been pulled them out, otherwise the periodic table would be too wide.
So
I'll
why
show
did-
you the
why did-
wide
Why
one.
did they put like a random chunk of it?
It's not random, these are all chemically similar to each other.
Oh, that's why they-
Because this is where we're filling up another sublevel called the F orbitals. Remember, this is the F block. And chemically, they're similar because what we're really doing is we're kind of backfilling electrons since they fill out of order. And because of that, these are all very chemically similar. Now, because we're 2 energy levels behind, the very next term I'm going to write, and this is the pattern we're going to follow. Even though if you look on this site, it's going to show you there's exceptions to the pattern. It's okay, we're not going to worry about it. But this would be 4, then F, confused.
Wait, why not?
Because F block,
You
Listen.
know what this is?
4th row, out of order, it's 2 behind. Really, it's the 6th row still, but we're 2 behind on these. So,
And then for D, it's 1.
yeah. So look at it this way. If N is the row I'm in,
I'm so
Then-
lost.
it's always going to follow this pattern. Just watch. The N will always be lined up with the S and the P. So you're always going to match the row with S and P. It's always going to be consistent. 1S, 2S, 3S. When you get to the D orbitals, it's going to be 1 behind when you're doing D in any of the rows. 3D, 4D, 5D, 6D. When you get to the F orbitals, it's always going to be 2 behind. 4F, 5F. That's it. So now, this is 4F, and there's 14 electrons worth I have to fill in. And once that's done, it puts me back to this position, which starts back at 5D again, right? Where this was 3D, this was 4D, this was 5D. 3D, 4D, so now I'm at 5D. And now I have to fill up all that chunk, and that puts me here. And then where am I at? I'm still in the 6th row, technically, for the P's. 14 is counting these purple ones. There's 14 elements worth. There's 7 orbitals.
Oh, wait, those two, why did they go back?
Yeah, those 2 yellow ones really plug in here.
Why are they there?
Yeah.
Because there's some debate as to where they really should be. Some people will say you put them in here first and then you start there. Don't worry about it.
Wait, so do you count it with the 14 in the bottom, or do you count it with
You
the-
count 14 in the bottom always. Some tables show those 2 as if there's 15, but they really belong in this slot. It's just showing you fill the F's before the D. Now after 6P6, we're here at 7S2. And then all we have left is 5F, 1, 2, 3, 4. Or we could have done this. So where's 6p6? I think it's radon, isn't it? So we could have done uranium as radon, 7s2, 5f4. Or that.
That's all?
Ta-da!
So all of that you just wrote in.
Word. But what I really want you to see from this is that the rules of quantum mechanics tell us that atoms have physical size and take up volume, not because of their protons and neutrons, which is most of its mass. It's because of the pattern that the electrons have to follow.
Wow.
Now, to finish up this lesson and let you practice it, because you need practice now more than anything, let me do this. Let me tell you that I'm going to ask you on Canvas, because that's where I put the assignment, to try to do the following. And I'll show you the easiest way I think you can do it. So the assignment on Canvas looks like this.
Oh, man.
Okay? So I made it a doc, so when you open it, you'll all have access to this. It shows you an example of each type of problem I'm asking you to do. Write the configuration, write it in the condensed form, write the arrow diagram, the orbital diagram, and then count how many unpaired electrons there are by just looking at this diagram. Here's what I'm going to show you. The easy thing to do, once you have this document, just copy and paste the terms and edit them. So you can literally, for example, if you're doing carbon, just look at carbon on the periodic table. You're going to see the configuration should be like 1s2, 2s2, 2p2. So from my example, just copy this chunk and just edit the 6 to a 2, and you'll have it in there. So it's easy because you're copying and pasting and then just editing. Now, I didn't go far enough for some of the bigger ones, so you're going to have to copy and paste terms and edit them in front. What I'm saying is, instead of trying to type all this from scratch, I gave you the ability to copy and paste the pieces so that you can just make edits to them. Okay? It should make it easier. But just to show you exactly what you're going to be doing to practice these skills, these are all the ground state configurations, including uranium. Haha. So the 1s2 stuff.
Are you kidding?
No, I'm serious.
That's the one we have to write all of them out for?
Yes, but again, you don't have to write it because I gave you the ability to copy and paste and edit.
Are you kidding?
That's kind of messed up.
Next,
Just do it on
There's
paper.
more?
the condensed
Yeah.
version
Me too.
with the noble gas. Next, the orbital diagrams. And then here, just counting. I'm sorry, this one is asking you to identify the element from the diagram.
You could do mine for now.
Like what symbol, what element is it? And it's really easy because if you just count the electrons, that's the atomic number. Or you can just look at the last term and find it on the periodic table. And then down here is where you do the arrow diagrams for these. I didn't give you a huge one because I thought that would be kind of crazy.
Oh, what a class that.
Here, just count how many unpaired electrons there are. That's your assignment. If you can do all that, you've got this. And you've got the next period to work on it, so make use of that time. Seriously. Otherwise, you're going to find yourself with a lot of homework. Well, from me. Some of you are behind on the online assignments.
Are you gonna say bye to them? Say bye.
Use your brain.